Hey everybody, in today's lesson, we're going to be learning how to add and subtract geometric vectors. So first, a little definition. People have taken physics. You would have hopefully seen this term before. But when you add two or more vectors together, what you're doing is you're combining those vectors to give a single vector called the resultant that has the same effect as the original vectors, applied one after the other. So for an example, consider the diagram illustrated below. If you walk 800 meters north and then 600 meters west, you get the same result as if you had just walked 1,000 meters in a direction roughly north 37 degrees west. You wind up at the same spot. That resultant vector is the result of adding those two vectors, the 800 meter one and the 600 meter one. You get the same effect. And so we usually denote the resultant vector by a capital R. Just going to add that to my diagram here. So today we want to determine, we want to get some methods for adding vectors together and then review mathematically how to figure out what the resultant is. Here's another example. So imagine you had 4 people, let's say these 4 people on the same team pulling left with forces of 100 newtons, 87 newtons, 95 newtons, and 102 newtons. And newtons is the unit of force. So they're all acting in the same direction. So those 4 people pulling those 4 forces, it's as if one person was pulling with a force of 384 newtons. Now, adding vectors like this that are parallel is really easy because all of these vectors pointed left and we just had to add up all the numbers. Even if we considered people pulling right, it'd be pretty easy too, because then we would just subtract the forces of the people pulling right and we can see which one was stronger. But when vectors aren't parallel, it's not as simple as just adding their magnitudes together. So we have to look at that. So I'm going to share with you 2 methods for adding vectors together. The first is what I was taught in high school, which is what I primarily use, the tip to tail method or the triangle method. So let's say you had 2 geometric vectors A and B. To add those 2 together, since we're adding, so vector A is first, and this does matter. Since vector A is first, so we draw vector A, or I'm just redrawing it. And then at the tip of A, where A ends, the head of A, we place the tail of B. So we've drawn A, and now from A, we draw B. Like so. And when we connect the tail of A with the tip of B, like that, we get the resultant vector. This is the resultant vector A plus B. And the arrow is so important. If I didn't have the arrow there, I might have the right idea of the magnitude, but without the arrow, you don't have a direction. And the vector A plus B in this diagram here points up and to the right, not down to the left. The direction is important. Remember, vectors have magnitude and direction. You need that arrow for geometric vectors to indicate a direction. Now, alternatively, I wanted to show you guys a different kind of notation for this. So let's say that this vector, A plus B, runs from point A to point B to point C. I'm just going to give names to these points. So hope you guys would agree, the vector AB plus the vector BC gives you a vector that goes from A to C. And now what I want to show you with this is that there's like a very useful kind of like just a visual tool for simplifying vector expressions where you have to express this way from a starting point to the ending point. As you can see, AB plus BC, if you have these B's linking up, it's almost like they cancel. It's not, they don't really cancel, but just like a visual aid. And the result is a vector that goes from A to C. So you can make use of that, and we will in various other applications, but just wanted to get that in there now. A second method is called the parallelogram method. And so maybe this method connects better with you. Let's show you how that looks. And then hopefully you'll be convinced that they're really the same method. So let's say we have vector A and B. This time we place the two vectors tail to tail. So I'm going to draw A. I'm going to draw B. This time I'm drawing B here, tail to tail. If you form a parallelogram with those two guys, then the resultant vector is the vector that goes across the diagonal, like so, vector A plus B. Right, because that'd be vector B on top, and that'd be vector A over here. And you can see you get the exact same result as the triangle method doing tip to tail, A plus B. But doing the parallelogram method illustrates an interesting property. So I'm going to switch to yellow to make this shot better. And maybe this was intuitive to you, maybe not though. We just drew the vector A plus B, but what the parallelogram method illustrates is that you get the exact same result as if you did vector B plus vector A using the tip to tail method. So this property has a special name. Numbers obey this property as well. This is the commutative property, and it works for vectors. For any two vectors, u and v, u plus v is the same as v plus u. So we are going to make use of that fact in other applications. Hopefully you guys are convinced that it's true. U plus v equals v plus u. The order of addition doesn't matter. All right, let's talk about what happens when we add a vector and its opposite. So say we have some vector A, and let's add its opposite. So there's vector A. The opposite vector, minus A, would look something like that. So it would have the same magnitude, just pointing in the opposite direction. So if we apply this tip to tail method and draw the resultant vector, what do we get? So let's use our tip to tail method. So I'm drawing A. From the tip of A, now I draw my second vector, which is minus A, pointing back. And I'm just leaving a little bit of space just to illustrate. But we wind up where we started with, and we wind up with a vector with no magnitude. I should actually not say no magnitude. It's a vector with a magnitude of 0. And that's okay. This vector actually has a special name. It's called the 0 vector. So just got some properties of the 0 vector here for you guys. So for any vector, A, if you add a vector and its opposite, you get the 0 vector. So that's illustrated in our diagram here. And this wouldn't have mattered if A pointed that way or pointed straight down. If you add the opposite, you're going to get right back where you started with, and you're going to get a vector with no magnitude. So this guy is called the 0 vector. Now it's different than 0. The 0 vector is a vector. 0 vector is not equal to 0. This is a vector and this is a scalar. So keep that in mind, that when you want to talk about the 0 vector, you should have that the vector symbol above it. If you don't, then you're referring to the number 0. And so here, if I had vector A plus negative vector A equals just 0 with no vector sign, then I'm saying when you add a vector with another vector, you get a scalar, which doesn't make sense. When you add two vectors, you always get a vector. The second property, kind of intuitive one, if you take any vector A and you add the 0 vector, you just get A. So this is the identity property for vector addition. And this is the same as numbers, right? If you add 0 to any number, you just get that number back again. So those might be kind of intuitive for you. And if that's so, that's okay. That's the identity property for vector addition. All right. We've talked about adding vectors. What about subtracting vectors? So regarding real numbers, one of the first things that you learn when you learn about negative integers, and you do adding, subtracting, adding a negative is equivalent to subtracting a positive. Does the same property apply to vectors? And the answer is yes. So my little diagram down here, I'll switch to something darker. So let's say I have vector A and I have vector B, and I'm interested in drawing vector A minus B. So just like with numbers, I can rewrite that as vector A. I can add the opposite plus negative B. So I might actually write that down as a bit of a, I think this is on your lesson sheet, but get this key idea in here. I'm not sure if it's on your lesson sheet or not right now. I don't want to pause the video to look at that. So subtracting a vector is like adding the opposite. Adding the opposites. So let's draw out what that looks like for this one. So I've drawn vector A, there's vector B. Maybe underneath vector B here, I can draw vector negative B. Now we know how to draw A plus negative B. There's A, there's negative B. We know how to add vectors together. I like to use the tip to tail method. I draw vector A. I'm adding negative B. So from the tip of A, I'm going to draw negative B, point something back like that. That's negative B. And my resultant vector, pointing relatively straight up, I'm not sure if it's exactly straight up, this is the vector A minus B. So subtracting vectors is not a big deal. You just add the opposite, and we've already covered how to add vectors together. There's the key idea. That's funny. So subtracting a vector is like adding the opposite. I did have it in there. All right. Let's do a few applications. So in this question, we have an airplane that's heading due south at a speed of 350 kilometers per hour, and it meets a wind blowing west at 100 kilometers per hour. And I hope we would all agree that if the plane is pointing south and the wind's blowing west, then the plane is ultimately going to kind of move in a southwestern direction. So I'm just going to draw that in a little bit. Sorry, that's my dog. So the plane's heading south. I'm going to call this just V. The wind is blowing to the west, like so. I'm going to call that vector W for the wind. And I mean, this is intuitive. We kind of all have an understanding that, the wind is going to blow the plane off course, right? The plane might want to go south, but the wind is going to blow it a bit to the southwest. And we're interested in, we call this R. What is this resultant velocity of the plane? What's our new speed of the plane? And which direction will it be flying? Because the plane itself, as far as it's concerned, it's pointing south. But somebody on the ground is going to see this plane kind of moving in some kind of southwestern direction. So we're interested in finding this angle here. And we have all the math tools to do that. So the size of that vector is 350. The size of that vector is 100. And this is just because this is south and west, makes a perfect right angle triangle. So the magnitude of the resultant vector is going to be the root of 100 squared plus 350 squared, whatever that is. And that angle, we have opposite and adjacent, we're going to use tan, will be the inverse tan of opposite over adjacent, 100 over 350. So you can do those along with me now. Shouldn't take too long. 100 squared plus 350 squared, and then square root that. So I got about, might double check that. I got about just 350, which seems really low. Plus 350 squared equals root. Yeah, that's better. I got 364. So the wind actually gives it a bit of a boost, speeds it up a little bit. That's kilometers per hour. And which direction is it going to go? So 100 divided by 350. Make sure you're working in degrees. Shift tan. So I got pretty near 16 degrees. And so we can say that the resultant velocity of the plane is 364 kilometers per hour in a direction south, 16 degrees west. So flying south, 16 degrees to the west. Now you may have done a problem like that in physics course before. You may have also done a problem like that in your grade 10 math course when you first learn about trigonometry and SOHCAHTOA. It's just really intuitive. Most of us have an understanding that the wind is going to blow something off course. So it's actually a consequence of vector addition. And we could have done the same problem whether the wind, the plane and the wind weren't at a right angle. We would just have to use the sine law or cosine law. Let's get some practice drawing some resultant vectors. So I've got three vectors here, A, B, and C. Vector B is the labeling is very large. When I converted that to a PDF, just made that big for some reason, but no big deal. So I would like you, with vectors A, B, and C, I'd like you to draw the following vectors. You can use a dashed line for the resultant vector, and don't forget to add the arrow to indicate the direction of the resultant. So I'd like you to draw three vectors, B plus C, A plus B plus C, and B minus C plus A. Doesn't have to be perfect. Don't get out the ruler protractor, but give those a go. You can pause the video and unpause when you're ready, or you can follow along with me right now. So B plus C. So to draw vector B plus C, we draw vector B. From the tip of B, we draw vector C, just going to the left. Complete the triangle. This is vector B plus C, and the direction is important. The direction will be up and to the left like that, from the tail of B to the tip of C. Okay, let's try B. So for B, we're adding A plus B plus C. So draw vector A. From the tip of A, we're adding B, so draw B straight up. From the tip of B, draw vector C to the left. And the resultant vector goes from kind of where you started to where you finished. This is A plus B plus C. Be something like that. And finally for C, vector B. So I'm just kind of mentally kind of thinking about where it's going to go. So I have some space. So there's vector B. B, we're subtracting C. So we'll add negative C, which would be going to the right. That's negative C. And then finally add on vector A, which is going up to the right like so. And so here our resultant vector is something like that. It would be going up this way. In your practice today, you'll be drawing some resultant vectors. Make sure you do it. Make sure you check your answers. Make sure you're comfortable with this method. Can't tell you how many students still just didn't grasp, had a hard time grasping this adding vectors. We're constantly adding vectors A and B by just drawing them together and then making a right angle triangle, which is not how we add vectors together. You either use the tip to tail method or you make a parallelogram and it's the diagonal. So please don't let that be you. Don't just draw two vectors and make a triangle. It's not how we find. That might give you the right magnitude, but it will not give you the right direction. So please, please, please do your practice. Let me know if you need a hand with anything. We have one little more exercise here for you guys to try. Just an exercise in identifying combinations of vectors. So here we have a parallelogram. So the 4 vertices, E, F, G, H, and then the where those diagonals meet is we'll call point J. So I would like you guys to try expressing each of these vectors as the sum of two other vectors. And you can do it in multiple ways, maybe 2 ways each. So for example, the vector that goes from H to F, I could write that 2 ways. I could write HF as a vector from H to G and then G to F. So I could write it like that, HG plus GF. And remember, that linking kind of strategy is that those G's cancel, and I know those are equivalent. Or I can go kind of up and then over, so HE and then EF. So HE plus EF. So in the same way for FH, and maybe you want to pause the video and give these a go yourself. So if I'm going from F to H, I could do it 2 ways. I could go from, well, I could do it multiple ways actually. I mean, I can go from F to E and then E to H. Those vector symbols, you know, or I could go from F to J and then J to H. Or FG to GH, that's 3. But they all have that property where that middle kind of links them up. And then from G to J, again, maybe try it on your own first and then unpause when you're ready, or you can follow along with me. But we just need to basically go to J from G via one other point. So you could go from G to F and then F to J. That works. Or G to H plus H to J. I think we're kind of beating a dead horse here. You could even go from G to E and then E to J. Many options. For part B, you're doing the same thing, but with vector subtraction. So give these guys a go, and you can, if you want to pause the video and unpause when you're ready. But how can we get there as a difference of vectors? So I'll share, I'll go do part 1 here. So, and you can kind of cheese these too, because you know you already have HG plus GF, right? Well, how can I write adding GF as vector subtraction? Well, I know the opposite of GF is just FG. So if I did HG and instead of plus GF subtracted FG, then that would work, right? Because subtracting FG is like adding GF, and then the 2 things link up. So in a similar manner, I could do HG, and instead of, or sorry, HE, and instead of doing HE plus EF, I could subtract FE. That's just one possible option. For FH, I could do FG. Instead of plus GH, I could do minus HG. Or I could do FE, and then instead of adding EH, subtract. Oh, that should be, that's a G. My G is getting sloppy. HE. From G to J, do it a couple ways. Go GF, and instead of adding FJ, subtract JF. I'll maybe throw one more on here. So GE, and then we added EJ last time. We can subtract JE this time. But yeah, I think you guys hopefully get the idea. That was kind of a lot of repetition there, but sometimes that's good just to make sure you have the ideas down. So in this video lesson, we learned about resultant vectors and how to add and subtract vectors. So what I really need you guys to be comfortable doing, like everybody has the trigonometry skills from earlier grades. You need to be rock solid in sketching resultant vectors. If this example made sense to you and you nailed it, you're in a good spot. If you had a hard time with this one, try it again. Make sure you do all those practice questions. So I've given you guys, as usual, a PDF with some practice, links and video solutions. Please give those a try. In our next lesson, we'll learn about scalar multiplication of vectors and then do some more applications and just get really comfortable with geometric vectors. That's it for today, guys. Hope you have a good one. We'll see you soon.